Hello everyone, my name is Andrew Kim and welcome to the fourth video of my AP Physics 1 review session. In this video, I will be going through Unit 4, which is Work and Energy. By the way, this is my third take of this video. I took two other videos, but I wasn't really satisfied with it. I thought I could explain things more concisely, so I'm taking it for the third time. Keep in mind. So let's get started. First of all, we have to talk about work. What does work mean in spoken English? Well, work can mean various different things. I worked on an assignment. I worked on a construction field. I worked for a paid job. It can mean various different things, but in physics, work, the definition of work is force times distance traveled. Now, I'll give you an example. Let's say you have an object lying on a surface and you pull this object with a force of 10 newtons for 10 meters. Now, if this is the case, then what is the work applied to this object? Well, that would be, again, work is equal to force times distance traveled. Force is 10 newtons, and the distance traveled is 10 meters. Thus, you get 100 Newton meters. That would be the work applied to this object. Now, one thing you have to keep in mind is that the unit of work it can be Newton meter. That also works, but Newton meter is simply, it looks kind of weird because you multiply the two units. So we substitute this into joules. We also call Newton meter into joules. So instead of saying 100 Newton meters, you can also say 100 joules. So the unit of work can be Newton meters, but it can also be joules. And you use joules more often, actually. So that's what you have for work. Now, what's interesting is that you have to keep in mind about the sign in front of work. In other words, there might be 100 joules and minus 100 joules, and you have to know the difference between the two. Now, when it's usually plus 100 joules, it means that the work is applied by the object. And when it's negative 100 joules, then it's the work that's done to the object because you're always talking from the perspective of the object. So if you say the object has done 100 joules of work, then you express it as plus 100 joules because we're always talking from the perspective of the object. And if the object is doing 100 joules of work, then you say it plus 100 joules. However, if the object is not doing work, but it's getting applied work from outer force, then you express it with negative sign. So you say negative 100 joule of work is done by the object, or plus 100 joule is done to the object. I hope you get the difference. But honestly, this is dealt more in detail in chemistry than physics. So in AP Physics 1, you would rarely see questions that ask the difference between the two. So now let's move on. Now that we talked about work, it's important to see the difference between work and energy and how they're related. Well, by definition, work is equal to the change in energy, which makes sense. Think about it. If you do some work, of course your energy would decrease because you've done work. So work is the change in energy. So, for example, if you apply work onto this block, if you apply, again, 10 Newton of force, 10 meters, then that would be 100 joule of work applied on this block. Now then, 100 joule applied to this block, which means this is the amount of work done. Thus, it also means the change in energy of this block. So that would be amount of energy changed in this block. So if you say initially the block was just staying still, if initially the block had 0 energy, then after this 10 newtons of pushing of 10 meters, the object would have an energy of 100 joules. Now what you can notice is that energy also uses the unit joule because work is the change of energy. So the change of energy and work should have the same unit, meaning that work and energy should both have the same unit, which is joules. I hope that makes sense. Now we can express this in equations. Work is equals to force times distance. For distance, we often use S. We use X, we use different things, but normally we just use S. And again, work is equal to the change in energy, which is delta E. And that's expressed over here. I'm pretty sure this is on your formula sheet, so you won't really have to memorize it, but it's important to understand this formula, to understand why this works. Again, if the energy changes, or if you do work, then of course your energy would change because you've done some work. I mean, if the energy stays the same and still you did the work, then that means you can do infinite amount of work because your energy does not change. Of course, which means if you do some work, then energy should change. And on the opposite way around also works. If you get work applied, then your energy should change. For example, if you eat food, you're getting energy applied, you're receiving work, then your energy would increase. So it's important to find a relationship between the two. And again, of course, the work is by definition force times distance, because higher the force is, of course, the amount of work that you do will be greater. And of course, the longer you apply the force, you will need to do more work. So that's why work is again equal to force times distance traveled. Now, one thing to keep in mind, it's a small detail, but you always multiply the distance traveled to force in order to calculate work, not displacement. Now, I've explained this in my previous video, in my first video, Unit 1 kinematics, but distance traveled and displacement are different. Displacement is basically where you started and where you ended. You're only looking at the difference in the location, not the path that leads you from one location to another. Whereas distance traveled is, for example, you traveled in this route, then distance traveled will be literally the length of this path, how long this path actually is. And of course, you would have to use distance traveled for work because, for example, if you use displacement, then let's say you rotate this box on a circular orbit once. If you use displacement, well, displacement of this action would be 0 because you start at this point and end at this point. You don't have a change in your location, thus no displacement. Displacement is 0. Which means if you use displacement instead of distance travel for this type of action, you would have 0 work done, which is obviously not true. You literally rotated the box, which means you applied work onto this box. Thus, you would instead have to use distance travel, which is literally how much the box has traveled, how long of a distance have you applied force onto this box. So please know that difference. Now let's move on. Now let's focus more on energy. Now it's important to remember that energy, or total energy, is conserved. Energy is conserved, total energy is conserved. Now this might seem really weird because I literally talked about the change in energy. I literally said the change in energy is the work done. But how can there be a change in energy if total energy is conserved, if it's constant all the time? If it's constant all the time, then there can't be a change. Well, the energy we're talking about here is the energy of a certain object, whereas total energy is the energy that the whole entire universe or the whole closed system has. For example, let's say you have a block that's initially moving, but it's moving on a surface with friction. So after 10 meters, it's going to stop. Now if you think about it, the energy that this box has will decrease because initially it had kinetic energy. It was moving, but at the end, you have 0 energy left. The box is not moving at all, thus it has 0 kinetic energy, it doesn't have energy left. The energy has changed. However, the total energy did not change. And when I say total energy, if this box slows down and stops eventually, that means that the box has done work onto the surface. How? Well, the box, by friction, has heated up the surface. It increased the temperature. It increased the energy of temperature-wise. Also, by sliding on a frictional surface, of course the box would have made sound, right? Think about it. If you slide a box on a surface, it will make a sound like kee or something like that. It made sound energy. In other words, yes, the kinetic energy itself of the box decreased, but the total energy, including kinetic energy, including sound energy, including heat energy, if you include all these energy that's present in this system, then that total energy will conserve. That's really important. Of course, you're not going to, you won't face a question that asks you to calculate heat energy and sound energy because that's extremely hard to calculate, but you will see some question that asks where one energy transforms its form into a different energy. For example, kinetic energy changing to potential energy, or potential energy changing to kinetic energy. And add the different types of energy to calculate the total energy, and use your knowledge that the total energy will conserve in a closed system. And in order to do that, of course, it's important to know the types of different energy. Yes, you have sound energy, yes, you have heat energy, but these will again rarely come out in Physics 1, and and the energy types that you will really face practically is only going to be the kinetic energy and potential energy, which is written over here. Now, let's talk about what these mean. First of all, kinetic energy. What does kinetic mean? It means something that's moving, right? So kinetic energy is the energy that's present on an object that is moving. So for example, if you have a box that's moving with a velocity of v and a mass m, then this box has a kinetic energy, and that energy can be calculated under the formula 1/2 mv squared. So the kinetic energy present on this box will be 1/2 mv squared, which is written over here. Now, the second type of energy is potential energy. But potential energy is like an umbrella term. Potential energy can mean various different types of potential energy. First type, and the type that will appear most frequently, is gravitational potential energy. And that is basically a potential energy caused by the gravity, caused by the force of the Earth pulling the object towards its center. And the formula for this can be calculated under the equation mgh, where m stands for the mass of the object, g stands for the gravitational acceleration, and h stands for the height on where the object is at. Which means that an object that is placed on somewhere it's higher will have more gravitational potential because its height, h, is higher. Now, I'm going to tell you why this formula actually works. Why the energy caused by gravity is equal to mgh. Well, that is because, again, energy, the change in energy, is equal to the work done, which is Fs. Now, F, which is force caused by gravity, is again F equals to mg. And S, the distance traveled in this situation, in vertical situation, in horizontal situation, distance traveled was literally as how long you moved. But in vertical situation, where we're talking about gravity, the distance traveled would be the height traveled, how high you're at. Thus, S would be h, meaning that energy, which is equal to work, which is equal to F times S, would be equal to mg times h, thus mgh. This is how you get the formula mgh for gravitational potential. Now, of course, you don't have to know this process of inducing the formula, but I want you guys to constantly think, why does this formula work? What does this formula imply? What physics meaning does this formula have? That's really important. The next form of potential energy is elastic potential energy. You can calculate this by 1/2 kx squared, where k stands for the elastic potential, the elastic potential, or the elastic constants of the spring or whatever you have, whatever elastic material you have. And x is the displacement, the amount of change in the length of the spring or whatever elastic object you have. But honestly, elastic potential would also rarely show up, so don't worry. And you have electric potential, but that is not going to show up at all, so you don't have to worry about that. So before I finish this video, I want to go through a very standard example where you have to know about conservation, where you have to use your knowledge in conservation of energy. So let's think about this situation. An object falls from height h, and it rotates on a roller coaster rail. And this point, let's say, has a height of 1/2 h. Now, at this point, the roller coaster has zero velocity. Let's say at this point, you just let the roller coaster go, so it doesn't have velocity right here. Well then, the only energy present on this roller coaster over here, would be the gravitational potential energy, which can be calculated by mgh. Now, let's think about the cart that's placed over here. If, under the assumption that there's no external force applied onto this cart except for gravity, if the cart is laid at this point, the energy of this cart would conserve. Of course, its gravitational potential energy would change, but the total energy, the sum of all the energy present, the gravitational potential, the kinetic, the elastic, whatever, all energy in total would stay the same. Which means at this point, the gravitational potential would be mg 1/2 h, because this time you're not at the height of h, but you're at the height of 1/2 h. So this would be your gravitational constant. And since this is lower than the initial potential energy you have, you would need a different source of energy that would make the total energy conserve and be equal to mgh. And that other source of energy, in this case, would be kinetic energy, 1/2 mv squared. Why? Because the roller coaster is moving at this point. At this point, you're just letting the roller coaster move down, so you don't have any velocity initially. But at this point, you will have the roller coaster moving, thus you will have kinetic energy, which is 1/2 mv squared. Thus, you can make an equation that mgh, which is the initial energy, is equal to mg 1/2 h times plus 1/2 mv squared, which is the final energy, which is the sum of the potential energy and the kinetic energy at this point. If you solve this equation, then you'll be able to find v in terms of mg and h. So this is how you want to approach. Always think about what is the total energy of the object, and think about what is the potential energy, what is the kinetic energy, what is the amount of energy of each source. And think that the sum of all the sources should be equal to the total energy present in the object or in the system, which should be constant all the time, because the energy conserves in a given closed system. Finally, in my third take, I finished the video without big confusion. Thank you for watching my review sessions, and don't forget to have a great day.